So far, in all the circuits that we have seen, the op-amps can be considered as ideal devices that have very high precision and very high gain. But in reality, the op-amps are not as perfect as we think. There are many designs made by different manufacturers. Some of these designs are better than others for one specific application. Some designs are well balanced and can be good enough for general purpose applications. Some op-amps are cheap and others are expensive. In this lesson, we will learn some of the considerations that we have to take when designing a circuit with op-amps. The first thing that we have to consider is that the output of an op-amp is constrained by the power supply voltages. Op-amps can be powered by a single power supply or by a combination of two power supplies providing a negative and a positive voltage. These voltages are usually referred as VCC plus and VCC minus. These voltages do not need to be symmetric, but we need to choose a range that allows to process our signals without distortion. There are two main kinds of op-amps. The ones called rail-to-rail can provide a voltage equal to their power supplies. For example, if the power supply is plus minus 12 volts, the output signal can also be plus minus 12 volts. Regular op-amps are not rail-to-rail. That means that the output voltage will be less than the power supply. For example, some of the op-amps I use are fed by a plus minus 12 power supply. In this case, I know that a safe output range will be around plus minus 10 volts. And for that reason, I try to never go outside those limits. In the diagram, you can see a simulation that uses a more complete op-amp model that captures the clipping behavior of the real op-amp. The op-amp is powered by a single power supply of 9 volts. The negative VCC is connected to ground. Since this is a rail-to-rail op-amp, we can see in the simulation results that with an input signal of plus minus 10 volts, the output is clipped to the range of 0 to 9 volts. As we mentioned before, op-amps are not perfect devices. In a previous lesson, we saw the formula for the op-amp. Here we can see that the voltage at the negative pin is subtracted from the positive. But in a real op-amp, there is a small offset value, so that subtraction is not perfect. In most cases, this offset is small enough that can be disregarded, but for some high-precision applications, that offset can be problematic. In such cases, we can buy op-amps that have a low offset value, for example, less than 1 millivolt. There exist as well op-amps that have a special pin where we can connect a voltage to compensate the offset. Another assumption that we made was that there was no input current into the op-amp. Real op-amps have a small input current on each pin. Similar to the offset voltage, in high-precision applications, this can be an issue. Op-amps have a limited slew rate. The slew rate defines the speed at which the output voltage of an op-amp can transition from one voltage to other. Let's say that the output voltage needs to quickly change from 0 volts to 1 volt. That change cannot be instantaneous. The simulation shows an example of a circuit that has a slew rate of 1 volt per second. This is very slow, but it is used for illustrative purposes. We can see that when the input jumps from 0 to 1, the output approaches to it with a limit of 1 volt per second. For example, the audio op-amps that I use have a slew rate of 20 volts per microsecond. This is very fast, but again, in some applications, it can be problematic and faster op-amps can be used. Another characteristic that is related to the op-amp is the bandwidth. The gain of an op-amp is not constant. It varies depending on the frequency. In the image, we can see about the plot of a common op-amp. We can see that for low frequencies, the gain is high, but as the frequencies increases, the gain is reduced until the point in which it's not amplifying any longer. The audio op-amps I use have a bandwidth of around 50 MHz. This bandwidth is high enough that they don't pose any problem for audio signals because they are in the range of 22 Hz to 22 kHz. For circuits that require processing higher frequency signals, it is possible to buy specialized op-amps with higher bandwidth. However, they are more expensive. One effect that we may find in some op-amp circuits is that when the output signal has fast jumps, under some circumstances the output can present oscillations as the ones shown in the plot. We are not going to cover in this course the cause of these oscillations, but we will see how we can fix the issues. In the previous slide, we saw that op-amps have a limited bandwidth. This behavior can be good to counteract the oscillations. There are op-amps called compensated that have some bandwidth limiting in place that helps mitigate these oscillations. If we encounter such oscillations, we can fix them by adding a small capacitor to reduce the bandwidth of the circuit. For example, in the diagram we have an inverting amplifier. I have added in the feedback path a small 10 pF capacitor. If we obtain the body plot of the circuit, we can see that the capacitor has limited the bandwidth of the circuit. At higher frequencies, the gain of the circuit is reduced. Limiting the bandwidth like this may not be a problem. For example, for audio applications, as long as we have a bandwidth above 22 kHz, the circuit will run fine. In a subsequent lesson, we will learn why a capacitor in the feedback path reduces the bandwidth. As a summary for this lesson, when designing an application that uses op-amps, we need to ask the following questions. What's the range of my signal? Based on that, we need to select an appropriate power supply and, if necessary, using rail-to-rail op-amps. What precision do I need? In most applications, high precision is not necessary, but when we need it, we need to pick op-amps and components with low offset values. How fast are my signals? Depending on the frequency of the signals we want to process, we need to pick components with enough bandwidth and slew rate. That way our signals are not affected much. Is my design stable? We need to consider that depending on the circuit, oscillations may show up. In that case, it is a good idea to limit the bandwidth of the design to the necessary range.